Okay, today, two topics. In the last class, I present three methods to construct an interpolation polynomial. Now, the first topic, I compare these three methods. A comparison of different interpolations. Second topic. Let me see. Second topic is second topic focus on Newton interpolation. The title of section 6.2 is divided differences. Okay, take a review about how we construct an interpolation polynomial. Okay. Take a review. Given a set of data, x2, xn. We want to find a polynomial passing all the data points. Okay, three approaches to do this. First one, write the interpolation polynomial, okay, as C0, C1, x, C2, x squared, Cn, right? Yeah, we want this polynomial passes all the data points. So pass the data point. Yeah. So yeah, pass data point. So Px0 is y0. Px1, y1, and so on. Pxn, yn. So we have how many equations? N plus 1, so many equations. You see, one equation, two equations. N plus 1. N plus 1 equations. How many unknowns? N plus 1 unknowns. The C coefficients are unknowns. Then solve this system of N plus 1 equations with N plus 1 unknowns. Then we can get the polynomial. But this approach highly sensitive to roundup error. Yeah, this approach to find interpolation polynomial, the book name is approach random interpolation. Yeah. Here. Yeah. This way to find a polynomial is called random interpolation. Because this approach highly sensitive to roundup error. And also when n is large, solve the linear system also expensive in terms of floating point operations. How many floating point operations? Order n cube, okay, order n cube. Say for example, if n is 100, then n cube is what? Million, 1 million, 10 to 6, 1 million. So solve 100 by 100 linear system by Gaussian elimination. Then you need to perform 1 million so many floating point operations, mainly multiplications. Okay, so expensive in terms of computational cost and sensitive to random variable. So in practice, people don't consider this approach to find interpolation polynomial. Second approach is called Newton, okay, Newton interpolation. Yeah. Number 2, Newton in interpolation. How to do that? Instead of express the polynomial in terms of powers, powers, x squared, xn powers. Okay, first introduce some special polynomials. Okay, say special polynomials. Q0, 0 is degree, is 1. Then Q1, polynomial of degree 1 is x minus x0. X0 here. Q2, this polynomial degree is 2. It is x minus x0 times x minus x1. And so on, and so on. And Qn, degree n polynomial, it is x minus x0, x minus x1, and x minus 1. Not x minus xn. Okay, now express the interpolation polynomial in terms of these special polynomials. Right. Polynomial that pass all the data points as C0 times Q0. Q0 is 1 plus Q1 times C1 times Q1, and then plus C2, Q2, and so on, Cn, Qa. Now, we require this polynomial passes all the data points. So Px0 is y0, Px1 is y1, and so on. Pxn is yn. Solve this linear system. But this linear system has special structure. Okay, if you write the linear system in matrix vector form, you will see it is a lower triangular coefficient matrix, lower triangular form. And here, unknown, C0, C1, unknown. And the right side is y0, y1, yn. Yn. This linear system easy to solve because forward substitution. Floatable operations for forward substitution is order n squared. Yeah, order n squared. Yeah, compare here. This is order n cubed. This is order n squared. And also this approach, the resulting unloads the solution not sensitive to random error. Yeah. Hey. Newton's interpretation, one advantage is computational cost is low. Second advantage, solution not sensitive to random error. The third advantage is if I want to add a data point, suppose for the old data point, I have obtained the polynomial. Now I want to add a data point to the existing data. We don't need to recompute the coefficients. How to do that? Yeah, yeah. Because I know usually the data points are collected from experiments. Yeah, we don't need to recompute this polynomial. Yeah, just yeah. Suppose for the old data set, we already computed this polynomial. Now I add a new data point. And I want a polynomial that pass all this new data set. How to do that? Yeah, easy. Okay. Yeah, this is I use different. P n plus 1 and how many data points? N plus 2. So the degree n plus 1. Yeah. This is a new. Okay, new. Now I write the new as the O. Yeah, O here. How about let me put n? N means a degree. Okay. O. Then plus. Just one more term. Cn plus 1. What's Cn plus 1? I will determine it. X minus x0. X minus x1. Then x minus xn. Yeah. This product, when you expand this product, you will see a polynomial degree. What is the degree of this part? N plus 1 degree. Right. This Pn. Suppose we already have this Pn. Right. Now, when I add a new data point, the new polynomials, write the new polynomial in this form. O plus a new term. Now let me determine this. Okay. How to determine this? Use this new data. I plug in xn plus 1 in x. Okay. Yeah. So plug in xn plus 1 in this equation. Left side should be yn plus 1 because I require this polynomial passes all the data points. Okay. Now here, Pn, I know Pn. Suppose I know Pn. So Pn xn plus 1. So yeah, I know this. Then plus Cn plus 1, I don't know. Cn plus 1, I don't know. Okay, now here, xn plus 1, x0, xn plus 1 minus x1, xn plus 1, xn. Now, yn plus 1, I know. This one, I know. This product, I know. Cn plus 1, I don't know. So solve this equation for Cn plus 1. Yeah. Move this to left side. And then move this product to left side. Then I can get Cn plus 1. So yeah. This is an advantage about Newton interpolation. When we have a data set, we have construct interpolation polynomial. When we want to add new data points to the old data set, we don't need to recompute the previous coefficients, the old coefficients. We don't need to forget. Advantage. This is now Newton interpolation, Vandermonde interpolation. One more interpolation in the last class I introduced. Lagrange interpolation. Okay, Lagrange interpolation. Number 3. Okay. Number 3. Let me see Lagrange. How does Lagrange interpolation? Now I want to find a polynomial. The polynomial passes all the data points. Okay, let me erase the new one. Okay, the new data point. Now to do that, first find interpolation polynomial that interpolate a special data set. Okay, yeah, very special. Yeah. X0, x1, x2, and xn. We give a name to them, call them loads. The loads and the loads here same, but the y values different. 1, 0, 0, 0. The polynomial that interpolate this special data set easy to be determined. Okay. The polynomial is x. Skip x0, x1, x2, x xn. This polynomial degree is n. Degree is n. Degree is n. So it's easy to see that this polynomial is 0 and x1, x2, and xn. Here. Plug in x1, x1 minus x1, 0. Plug in x2, x2 minus x2, 0. Plug in x0. This polynomial, its value is not 1. I want the value 1. So over x0, x0, xn. Yeah, this polynomial easy to see. Passes all the data points in this set, data set. Give a name. L Lagrange. Zero X. Similarly, for a second special data set, x0, x1, x2, x3, and so on, xn. Yeah. This second special data set. 0. X1 is 1, 0, 0, and 0. Corresponding interpolation polynomial is interpolation polynomial to this special set is not this time. Skip x1. Okay. X minus x0 times x minus x2. Okay. Not x1. Skip x1. Now x minus x3. X minus xn. Yeah. This polynomial degree is n. And values at the roots are 0 except at x1. At x1, we require the polynomial, the value is 1. So I divide, okay? Plug in x1. So yeah, x1 minus x0. x1 minus x2. x1 minus x3. x1 minus x8. Okay, yeah. Call this, give a name. This is a L1 x. Okay. After we have L0, L1, L2, and so on, Ln. Okay. Then the polynomial for this, the original data set is, yeah, P is just a Y0 times L0. Y1 times L1. And so on. Yn times Ln. So Lagrange interpolation doesn't need to solve linear system. And highly stable, okay? Completely not sensitive to random error at all, okay? This is our advantages. One more advantage for Lagrange interpolation is, okay, yeah. A data set is an experiment. I don't know what kind of experiment, say chemical experiment. Yeah. If you want to do experiment again, yeah, but with the same loads, yeah, here. Yeah. This is a experiment 1. Experiment 1. Experiment 2. With the same loads. Then we have new y values. New, okay, y values. Corresponding with the same loads, we do, experiments again and again. Then Lagrange, in this case, Lagrange interpolation is very convenient. Why? Polynomial then interpret this table is this. Polynomial that interpret this table is what? Is this. Yeah. Just a replace, y0, y1. That's it. You don't need to, recompute the interpolation polynomial. Do you see what I mean? So we have two data sets. Right? After we have L0, L1, L2, yeah, this is called cardinal functions. The both, give a name to these polynomials, cardinal functions. After we have cardinal functions, then no matter how many data sets we have, okay, it's very easy to construct interpolation polynomial. Just replace, y0 with the new y values. Very, is an advantage of Lagrange interpolation polynomial. Yeah, this is topic 1. Compare these 3 approaches to construct interpolation polynomial. Yeah. Okay, now second topic today. Second topic, section 6.2. Let's focus on Newton interpolation. Why Newton interpolation? Because Newton interpolation is easy to extend to solve other more complicated problems. So let's focus on Newton. Okay, Newton. All right. Topic 2. Section 6.2. The title is divided differences. Okay. We have a set of data. A set of data. Here, function value, right? Function value. This is f x0, f x1, f x2, f xn. Now, express the polynomial, interpolation polynomial in terms of some special polynomials. Yeah, special polynomials. 1, Q1 is x minus x0. Q2 is x minus x0, x minus x1, and so on. QA is x minus x0, x minus x1, x minus xn minus 1. Yeah, pay attention here. Xn minus 1, not xn. Okay. Because x0, x1, xn minus 1, this product, the degree is n. Now, the polynomial that passes through this data point is interpolation polynomial. This is a interpolation polynomial. In Newton's form, okay? Interpolation polynomial is one and only one interpolation polynomial. But you can write it in different forms. In Newton form, in Lagrange form, in power form, right? C0 plus C1 times x1 plus C2 times x2, power form. Interpolation polynomial in Newton's form is this. Yeah, this is a Pn, degree n. is C0 Q1 Q0 plus C2 Q2 plus Cn Qn. Okay, now plug in x0, x1, x2 into this polynomial. Solve the linear system. It's easy to see that C0 is equal to function value at x0. C1 is this. Okay. Is this. Yeah, easy to determine. Okay. Now C2 maybe not so always. Okay. Yeah, C2 not so always. But we are sure. Okay, sure. One thing is sure. Okay, C0 depends on f x0. Doesn't depend on C0 doesn't depend on f x1, f x2, and so on. Only depends on f function value at x0. And C1 depends on f x0 and f x1. Only depends on the function value at these 2 points. And so on. One thing, yeah, this thing is sure. How about CK? CK, a general coefficient. CK depends on f x0, f x1, and so on. F xk. This. Now, to emphasize this dependence, we write CK, yeah, to emphasize, CK depends on function values at x0, x1 to xk. Okay, we write CK. Let me introduce a new notation. Yeah. F, of course, depends on F, of course. Yeah. Okay, brackets. Okay, brackets. And then x0, x1, xk. New notation. And also give a name to this new notation, because it turns out that this new notation has not just interpolation polynomial. Yeah, here I'm talking about interpolation polynomial in Newton's form, not just in this topic. In other topic, it turns out that this notation has other applications. Deserve to give a name. Okay, yeah, call this. Okay, divided difference of all the k, because all the k of the function f, the function f. Why we call give a name divided difference? You see, look at C1. Yeah. This is a difference. Divided difference. Difference over difference. Divided difference. This is a divided difference of order 1 because k is 1. Order k. It turns out that this notation has other applications. So we give a name. Okay, now with this new notation, Newton interpolation polynomial can be written as what? Can be written as here. The Newton interpolation can be written as f x 0 times q 0. Then plus this is a f x 0 x 1 times q 1 plus c2 f x 0 x 1 x2 q2, and then plus here f x 0 x 1 x2 xn qn. Okay. The coefficients we can solve linear system, a lower triangular system, to obtain the coefficients. But we can also, by using this notation, to get the coefficients. Yeah, there is a formula for dividing difference interpolation. Yeah, formula. Before I present the formula for divided difference for this notation, let me make a remark. Interpolation polynomial is one and only one. No more. No more. And then that is Newton. Let's say let P polynomial be an be the interpolation polynomial. Interpolation polynomial of a data set. A data set. Yeah, I have erased the data set. This polynomial is one and only one, no more, just one. Just one. It can be written in different forms. This is an interpolation polynomial in Newton's form. So P must be equal to the Pn. Must be equal to the Pn. Okay. This Pn, the leading coefficient is this. This is this polynomial degree is n. This is degree 2. The coefficient of the highest degree term is called leading coefficient. So leading coefficient is this. Now compare the leading coefficient Leading coefficient of this is an. Leading coefficient of this is f x0, x1, xn. They must be the same. So interpolation polynomial its leading coefficient must be divided difference. How about the other coefficients? No guarantee. Okay, check. How about A2? A2, pay attention, log equal to f x0, x1, x2. Only the leading coefficient is dividing difference is this. The other coefficients, okay, no. Say for example, A2 doesn't equal to this. Yeah, this is a remark. Hey, now I present a formula to compute divided difference. Yeah, here. Let me erase this part. Okay. Yeah, the board is too small. It is a film. This film is about divided difference. Okay. Define fxi is equal to function value and xi. What is I is 0, 1 to n. Yeah. You need to remember the data set again. X0, x1, x2, and xn. Okay, now this is a divided difference of order zero, just one point, order zero. Okay, then the formula, yeah, how to compute this? How to compute this? This is the formula is order n divided difference is equal to order n minus 1. Okay, yeah, here. x1, x2, xn. Yeah, this is the order n minus 1. Yeah, minus order n minus 1. And then over the last point, xn, minus the first point, x0. Let me show you one example about how to use this formula. So, see, divided difference is coefficients. Now I can use this formula to find out all the coefficients of Newton interpolation polynomial. Take a look at one example. Here. Here. Example 1. Find interpolation polynomial to the following data. Following data. 3, 1, 5, 6. The lobes x0, x1, x2, x3. The lobes not necessary to be in increasing order. Okay, can be arbitrary order. Function value 1. Function value is function value. Yeah. 1, -3, 2, 4. Okay. Now I want to determine the coefficients in Newton interpolation polynomial. I use this formula. Use the formula here. Here. Okay. I don't have space. How about here? Let me erase. Now let me make a table. Here, this table. X0 is number 3. X1 is 1. X2 is 5. X3 is 6. Now, first column, F X0 is by definition, okay, function value at X0. So function value at X0 is 1. Yeah. What is F brackets X0? Yeah, here. The coefficient, this coefficient. And then F brackets X1. By definition, function value at X1, -3. Yeah, function value negative. And then F X2. Number 2. F X3. 4. Now, by this formula, I can compute F X0, X1. What? Yeah. Here, this coefficient. I can compute 1. That formula over there. F X1 X0 minus X1 X0. Yeah. Formula. Yeah. So what is this? F1 -3 minus 1 -4. And then over 1 minus 3 -2. So 2. Yeah, this number is 2. Yeah, here 2. Okay. And then here the next is F X1 X2 by formula X2 minus X1 over X2 minus X1. So this is 5/4. Okay, also compute this. Yeah. F X2 X3. This is number 2. Yeah. These 2 numbers for this. Okay. This 2 for this and this 2 for this. Okay, now for this coefficient here. This is F X0, X1, X2. How? Formula over there. This is F X1, X2 minus F X0, X1. Then over the last entry, X2 minus first entry, X0. F X1, X2. I got it here. F X0, X1. I got it here. 2. Then X2. Yeah, X2 minus X0. So the number is -3/8. This is -3/8. Okay. Now this is a degree 3 polynomial. So similarly, f x0, x1, x2, let me erase. I don't have time. Then compare. Similarly, compare x1, x2, x3. How? From here, from this number and this number. Yeah, complete it. Now, finally, from this two, compare what? Here, compare f, x0, x1, x2, x3. Yeah, the leading coefficient. For details, take a look at my notes. Yeah, take a look at my notes. So I stop here.